We'll now discuss mass spectrometry or mass spectroscopy. Both terms are usable. So that you can interpret mass spec traces to get an isotope mix of an element and weighted average atomic mass. We're not going to talk about molecules in a mass spec. The problem we have is that we know all elements are fundamental building blocks of various compounds. We also know that Boscovich was correct and Dalton was wrong. Dalton thought all atoms of a given element are exactly the same as every other atom, and that's not true. Because, as Rutherford discovered, the nucleus contains most of the mass, and we know it contains both protons and neutrons. For a given element, the protons are always the same. For instance, lithium is always 3 protons. But there can be different numbers of neutrons, and that changes the mass. Atoms with differing numbers of neutrons are called isotopes of the element. For example, bromine has only 2 naturally occurring isotopes, the 79 and the 81, and what you see here is the natural abundance of each, and the atomic mass, which is not exactly 79 and 81, because of what you learned in nuclear chemistry is called the mass defect, not to be concerned about at this time. Now, looking back at Chemistry 1, using your weighted average formula, determine the weighted average atomic mass. Just to remind you, you'll multiply the decimal equivalent of this, 0.5069, by the atomic mass, and that's the contribution of the bromine 79, and you'll add to it the product of the decimal equivalent 0.4931 of the 81 isotope, multiplying by this atomic mass, and you should get a mass very, very close to what you see on the periodic table. Now, why would it be difficult to separate an element like bromine into 2 different isotopes? Well, look at the percent mass difference, and you see that it's very, very small. You're looking in most cases at less than 5% difference. And remember, of course, the chemistry of all bromine is exactly the same, so you can't separate isotopes chemically. Nuclear scientists need to separate the useful U-235 uranium from the U-238, which is only useful really to make bullets. The percent mass difference of 3 over 235 is just a little over 1%. So you do take advantage of the fact that the U-238 is more massive, and you use centrifuges to separate. That's for large quantities, quantities greater than a few grams. But for small quantities, the mass spec gives excellent separation. In fact, it's coupled with gas chromatography. Now, moving charged particles in a magnetic field, and you can look that up on YouTube and see an electron beam in a magnetic field there, and you'll notice that the moving charged particle is deflected by the magnetic field. It's bent. This is a picture of a mass spec from Thermo, one of the fine instrument makers that serves this market. And here is a diagram or schematic of the mass spectrograph. We'll go over it a little bit at a time. First of all, we have to have very, very high Gauss magnetic fields and nearly perfect vacuums in this instrument. Here, the sample is very rarefied, has very low pressure, less than 1 torr, and it is introduced into this, again, it's all evacuated, this chamber where it is ionized. You heat it up, strip off some electrons, maybe more than one, and you pass it through a slit, which in this slit there's charges. Since these are positively charged, they're attracted to the positive and repelled from the negative, and they get going very, very fast through the accelerator. And as you can see, a mixture of different colored dots, and therefore a mixture of different massive isotopes, are here. If you think about big cars and little cars racing on a curve, you know the big car finds it harder to turn, and so it's going to be deflected out less than the smaller cars, which will be deflected down. Ultimately, though, you'll get all of the impact of the ions here on the detector. The light ones will be over here on the downfield, and the heavy ones will be up here. The detector then is wired so that you can read out on the computer screen the mass, light to heavy, versus the number of strikes on the detector, which is called a signal. And with small numbers of strikes, you have a small signal. With large number of strikes, you have a large signal. So the more of the isotope there is, the higher will be this line. And I think you can see that that's how we affect a separation and get an idea of the relationship between the mass and the number of isotopes by counting the number of strikes. We won't give you the mass spec op. You can look that also up on the internet. But this is the typical pattern that we see in this case for our old friend bromine. Now, just a point here. They have measured relative to the highest number of strikes, the highest incidence of bromine ions striking the detector, and they call that 100, and this 81 isotope has fewer. So if you want a percent incidence, you would have to add the 100 to the 97.3 to get 197.3. The numbers are relative to the maximum gain on the scope, so you need to make your own fractions if you want percent composition. So with a denominator of 197.3, the numerators are 197.3, you should be able to calculate the percent abundance of the bromine, and it should come out very, very close to what you had on the previous slide. This is strontium. There are 3 isotopes, as you can see, but here they've actually graphed the relative abundance so that this roughly 82, this 10, and this 7 or 8 add up to be very close to 100%, or 1.0 decimals. And you should be able to calculate then the weighted average mass of strontium by, and of course here's the 84 here, which is just 1%, by multiplying 0.01 by 84, 1% is 0.01, adding the 10%, 0.1 times 86, the 7% or 0.07 by the 87, and then the 82% or 0.82 by 88. If you add up those 4 numbers, you should come up with a weighted average close to what you see on the periodic table. Here is zirconium. You might want to turn off the video so that you can do calculations. This is relative abundance, so all of these should add up to 100. Here's about 53%. Here's maybe 12, and perhaps 18, and on the 94 maybe 19%, and then on the 96 looks to be about maybe 3 or 4%. So you should be able to do these as well. Here's the mass spec for boron. There are only 2 isotopes, a 10 and an 11. And the 10 isotope looks to be, if this is 1020, looks to be about 25. But notice this goes to 100. So this is not the percent abundance, this is the relative abundance. And if you wanted the percent abundance, you would have to add up this 100 to this roughly 25 use that as a divisor and then take the 25 and divide by 125 to get the 10 isotope percent, and then this 100 divided by 125 to get the 11 isotope percent. Now for chlorine, I'll just show this to you and you can discuss it and talk about it. And if you look very carefully at this, you might want to think about the element formula before you determine in your own mind how many isotopes of chlorine there are. Remember what the element chlorine comes at, what kind of molecule it is. This is a really tremendous table from Perk and Elmer, and it gives you the trace that we get on the mass spec for just about every element that's known. Some of these elements are synthetic elements, but we don't have enough of them to do a mass spec for, so we don't have a trace on these. They're radioactive. They don't hang around long enough to get a good mass spec. But the rest of them we do, and I would encourage you to look at this a little more so that you can compare this to what we have in maybe some of the other slides.